All right, well, thank you, Nicholas. All right, and good to see so many people here. Some of you may have seen some of this material, or some of these subjects before, but we'll see. If I need to speak louder, let me know, wave at me at the back, just because I'm likely to slow, or if I need to slow down, just let me know. I'm going to be covering basically what EPICS is. I'll talk about the history, what it does, how it does it. As Nicholas said, talk about the community and where it comes from and the sorts of things that the community does and how we manage ourselves. And talk about then the ecosystem, the collection of tools that we use here at the APS, both in the Accelerator side and, as far as we know, on the Beamline side, at least for those that are BCDA run Beamlines. And then I have a few slides on alternatives for some of those tools that we don't use here, but are used at other sites. So there are possibilities that we might want to look at in the future. So starting then, so what is EPICS? So, I mean, a lot of people say, well, I know what EPICS is, or I've come across something like that. It's basically three different things that all come under the same name. So EPICS is the name of the collaboration, the group of people, labs, and sites that are actually making use of EPICS. It's the name for the architecture, the way that we actually put our machines together, so that you have IOCs or front-end computers connected over a network to workstations in the control room or around your offices, and network protocols and so on. So EPICS is the architecture that entails, that was developed for that. And it's also the name of the software toolkit, the collection of programs that are running in those various different places, so on the front ends and the workstations and the servers and so on. So if we start with the collaboration, this is just a small number of the labs that are using EPICS, that have used EPICS and are reliant on it. So there's quite a lot of different places on all continents, except for, I'm not aware of anything in the the South Pole that's using EPICS yet. But if anybody knows of anything, I'd be interested to hear about that. But other than that, EPICS is used at labs throughout the world. So we have an international group of laboratories and companies. There are companies that are selling things into the EPICS community that use and develop it. But as I said, there are many more than I could actually show those logos on that slide. And I know I've identified at least 24 countries represented, but I probably missed a few. So it's really amazingly widely used. We have a mailing list, the Tech Talk mailing list for users and technical discussions and so on. I did a count the other day, and there are over 700 subscribers to that mailing list. So that's, again, showing you how much widely we're actually used. We have twice yearly meetings where we discuss progress and new projects, what's going on. The location for those meetings moves around between Europe, America, and Asia Pacific. So the next meeting coming up is in France at the end of October. The meetings are basically open to anyone who wants to come. Typically, we get somewhere between 100 and 150 attendees in the recent years. And they sort of vary slightly. The people coming tend to be geographically close to where the location is, but there are a number of people that do come from anywhere. Roughly 75 presentations, that sort of number, over the 3-day meetings, and then we usually add training and other meetings going on. So there's usually a short version of beginner EPICS training that happens for sites that are just coming on and that need some to get started with EPICS. And then we also, the developers use that time. We have 1 or 2 days of meetings where we're actually meeting with other developers and saying, okay, how far have you got? What are you working on? How's this part? And we can then talk to each other and work out what we need to do next, sort of thing. And then we also collaborate during the year outside of the meeting times then Between users, many labs share software development effort, so I'll talk later about the version 4 development which is going on. So there are developers there from Brookhaven, ITER, Slack, and the Michigan State and so on. So they're basically people from many different places that are collaborating on that. And we basically meet and discuss through mailing lists and Google Hangouts and so on. But also anybody can assist with finding bugs, and then EPICS is portable with a number of operating systems, but it's relatively easy to add to new things if there are, or if there are problems with new versions, then anybody can help. And also answering questions on Tech Talk is actually a very useful thing where I don't have time to answer as many questions now as I used to, so it's helpful for other people to come in and do those things where you know specific answers. So the second definition then was EPICS is our control system architecture, and the architecture actually is sort of represented by the logo, because we have client applications on the top, server applications down below, and the network in the middle. So it's basically saying this is the sort of the basic structure of the architecture, where you've got connections to the machine at the bottom and connections to the users up the top, and we have a network in between. So the servers are providing something called a process variable, which is a named object which holds a piece of data that's associated with the machine in some way. So it may be a status, it may be a readback value, it may be a set point, it may be parameters associated with control loops or those kinds of things. And to be able to talk to a server, all a client needs to know is the process variable name of the piece of data that it wants to access. And that's the simplest really way of basically it's really simple to connect to the machine. You just need to know what's the PV name that I need to talk to. So here are a couple of PV names from the APS Accelerator. So we have the current in the storage ring. So we can ask for that current. You've give that PV name in on the Accelerator network, and you can get back what the current is at the moment. And store it. So similarly, there's the storage ring lifetime available in minutes. There's another PV name. So that's all you need to know to actually get that information. As well as just a value, though, a process variable has other attributes associated with it which you can request if you explicitly ask for them. So that will be things like the engineering unit string. So here I've said the current is in milliamps, but it's the milliamps is not part of the value. The milliamps is this engineering unit string, which you can request if you want to. We also provide a timestamp so that you know when this data was generated, so that you can tell, the storage ring hasn't actually been running, so we're not actually reading the current, so this data may be an hour old, or something like that. The data may have problems. It may not be a value which is a good value, so there may be alarms associated with it. So there's an alarm status and severity associated with each value that you can fetch. And then there are other things like operating ranges, the standard low to high range that you expect this value to range between. Control limits, how high and how low you can adjust it to if you have permission to adjust it, and so on. So that's the basic structure of how we communicate, is just using those channel access process variable names. Pass them to channel access, and it can tell you about what the data type is, and you can request then the value and any attributes, the specific attributes that you want. The third part then is, the third meaning of EPICS is the software toolkit. So we have this whole list of, there's a subset of the client programs there, channel access in the middle, and the IOC software. So there's lots of different things that can be made to run down on the IOC. So the toolkit is basically the collection of all these different programs. You can also write your own servers. So in most cases, IOCs are used as the servers, but you can also write your own if you have additional data that doesn't really fit into an IOC. It's possible to make that data available over the network by writing your own software. So when you install EPICS, then you don't actually get the control system. All you get is the collection of tools that you happen to have installed. I mean, there's the core thing, which is EPICS base, but then all the other parts are optional and need to be installed separately. And as I said, we've got hundreds of pieces of software that make up the toolkit. So some of them are individual programs, standalone programs that perform specific tasks, like creating and running the graphical user interfaces, or archiving data, or monitoring for alarms, and so on. We have things that are code libraries for talking to specific pieces of hardware. Those would usually be code that would run down in the IOC. So you've got device and driver support to talk to PLCs or oscilloscopes and those kinds of things. And also we provide software for many of the common programming languages, so that you can actually write your own code to control your equipment in C, C++, Perl, Python, Java, MATLAB. In some places that's fairly heavily used. There is a C# interface, LabVIEW in some places as well, and so on. Now, almost all the EPICS code is open source, and the EPICS open license is the main one that's used for the core software, which is pretty BSD-like. Basically, anybody can download it and modify it and do anything that they like with it. There are some tools that are use the GNU GPL or the LGPL. So those have specific. If you make use of those tools, you just need to know if you make modifications that you are obligated to hand out copies of the source code if you hand out binary versions. So I need to be aware of what the licenses are. But in most cases, the EPICS stuff is run under the EPICS license, so you can do anything you like with it. And so creating a control system, because there's all this software already available, creating a control system can in many cases be done just by downloading software, building it, installing it, and configuring it. And you don't actually have to write any code at all. So you don't actually have to write C, C++, Perl code for a lot of cases. So many of the things that the controls group do don't involve writing code at all. They're just configuring parts of the IOC, writing record descriptions, writing screens that can talk to it, but not actually having to write code as such. There may be gaps. You may want to use a piece of equipment which doesn't have a driver yet, and so there are ways that we make that easy for if you're talking to something over a serial port or over a TCP/IP socket. We have tools that make it easy to actually talk to those kinds of devices to reduce the amount of code you have to do. But in some cases, you might end up having to write software. But actually, there's less and less of that's necessary nowadays. So let's move on to a little bit about the history of EPICS. The history, EPICS started a long time ago in a place far, far away. But maybe not quite that far away or quite that long ago. Not even as far as the movie, actually. So in 1988, there was a workshop run at Los Alamos National Lab called the Accelerator Automation Application Toolkit Workshop. And apparently that was a rather exciting meeting. I think, from what I can gather, it was called by Los Alamos, who were to bring together accelerator controls people from around the world. They were charged with building the ground test accelerator. And the ground test accelerator was part of Ronald Reagan's Star Wars, Strategic Defense Initiative program. And they basically wanted advice on what's the best way of building a control system for this thing. So the workshop was called to actually set direction for their controls group. What kinds of development, what direction should we actually put this development in? And out of that, that controls group created this thing called the GTA control system, or GTACS. And so the main guys working on that were Bob D'Alessio and Jeff Hill, but there were a number of other people at Los Alamos who were responsible and provided different parts. But the main two who are still in the community are Bob and Jeff. Now, at that meeting, there were some people from Argonne. I'm not quite sure exactly how that fitted to the original design of the APS control system, but the APS control development was coming up in the following year. So they were actually, at least some people from Argonne went to that meeting. And apparently there was another meeting as well at CERN, which had additional interesting discussions going on. So when APS started building the APS control system, they sent Marty Kramer to Los Alamos to work with the GTACS team for 6 months, because basically GTACS people said, why would we want to collaborate with you? What are we going to get out of it? And so what they got out of it was Marty Kramer working on their project for writing software for them for that 6 months. But in that time period, Marty was then learning all about this GTACS software and working out how it would work here at the APS. So he came back and convinced everybody here that this was the ideal basis for a collaboration and for the APS to use for the control system. So they basically continued development afterwards. The software was renamed to EPICS and presented at ICALEPS in 1991. And at that point, a few other labs started joining in. So Lawrence Berkeley Lab, Steve Lewis came on. Dave Gerd was the controls group leader for the superconducting super collider, and that was what was interested in using it. And Chip Watson at Jefferson Lab for CBAF. So they started in '92. Around that time, or shortly after, they actually managed to sell commercial licenses for EPICS and negotiated with some companies. So those companies basically did some additional development and managed to sell that to various places in the process control thing. But they also continue to hand out licenses to collaborators to other labs. And all that required was you had to sign a legal agreement with Los Alamos to actually make use of the software, but it didn't cost you anything. So, I mean, I worked at the Royal Greenwich Observatory in the late 90s, and we had to sign the agreement to get hold of the software. You had to have VxWorks to be able to use it at the time. Another thing is APS was an early adopter for HTML and the World Wide Web, and so the first EPICS website was one of the earlier web servers around. So in August 1993, that was one of the early web servers available on the network. And sort of between then, basically development continued, more features were added, more robustness and portability and so on. Replaced the original IOC had the database files were all in binary. That was converted to ASCII. We continued to add new hardware support for new kinds of hardware, and the community grew as new people decided they wanted to use this stuff. But then up until 2002, you still actually had to use VxWorks to run your IOCs. There was no alternative. But in 3.14, Marty decided that it really needed to be made portable and be able to be used on other operating systems. So he worked with Jeff Hill and Janet to make that happen. And then at about that time, Eric Norum at the Saskatchewan Accelerator Laboratory was looking at development for the Canadian light source, and he ported it to run on RTEMS. So you now have the choice of VxWorks or RTEMS for your real-time systems. In 2004, we managed to convert the code from this restrictive license from Los Alamos to an open source license that DOE approved, and so now the core software is freely redistributable. But before that, you were not allowed to pass it out to anybody else. And currently, we really don't know how many. I have no idea how many people are using EPICS or the full list of who is. The last numbers that I have were just before we went open source in 2004. We had 170 licensees. But so in the last 10 years, that's grown significantly, and as of as of today, about a month ago, I do count the number of people who download EPICS-BAST, and I had 2,000 downloads in a month recently. So that's a significant amount of usage. So that's the end of our brief history lesson. What does it do, or even what can it do? And the answer to that is pretty much anything that you need from a typical distributed control system. So we've got the ability to do remote control and monitoring of technical equipment, obviously essential for out here. It does data conversions and filtering. We can do closed loop control, and there's both slow loops and fast loops. If you have hardware support, you can do some kilohertz rate feedback and control that. We have access security. It's not hacker-proof security, but it keeps the honest people honest. We can apply constraints about operations of equipment. We can detect alarms and report them and log the alarms. We trend the data, archive data, and do archive retrieval and plotting of that stuff. Sequencing of operations, so if you've got complex things that need to happen to bring the accelerator up or park your telescope mirror, then that's all possible. We do mode and facility configuration control, sort of save restore. I've got a working setup here. I want to save the values, my configuration values, so that I can come back to them later if I've messed something up. Modeling and simulation is also possible, and it's actually happening a bit more nowadays, the newer versions. And obviously data acquisition and image data, so area detector that was mentioned earlier, that's obviously a very growing area of image processing and image manipulation, and data analysis. So sort of quite a collection of things. How does it do it? The sort of the basic architecture then, we have our equipment down here that we're going to connect through the technical equipment, your power supplies, your beam position monitor, electronics, your vacuum gauges and whatever. We connect those through a computer interface to the IOC, which is the green box. So this is, going back to that logo, this is one of those boxes down the bottom half. So the IOC then is a channel access server, and it provides process variables. And in this case, we have, my pointer isn't working, it doesn't come through, okay. So we have a number of named process variables here, one for the power supply, a couple for the beam position monitors, and we've got the vacuum gauge reading and so on. We also have channel access clients up on top, where we can actually access that data, and you can have multiple clients running, connecting to different data items at the same time. And so the clients then talk to, using their channel access client library, talk over the network to the server. They provide the name of the process variable they want to see, and then can access the current value and can make changes for those channels that they're allowed to, and so on. So that list of functions that we talked about, the things happening down in the IOC are these things like the data conversion, filtering, the alarm detection. Access security is a function of the IOC, anybody can write a channel access client program. They don't have to do anything special to prevent access to the data. Closed loop control obviously is going to happen in most cases down below. You keep your operational constraints down here. We do the sequencing in the IOC, although that can also be done up top. And similarly, we can do data trending and archiving at that point. In the client end, then we're obviously doing remote control and monitoring. We log our alarms, so we detect the alarms in the IOC, but then we need to log them and do any reporting up on the client side. We can also do closed loop control up there. So I said, so as long as your control loop is not terribly fast, it's quite feasible to run that remotely. And similarly, you can also keep operational constraints up the top. And as I said, sequencing can also happen up there as long as it's not particularly fast. You're not worried about the network delays. And similarly, the data trending and archiving, simulation and modeling and configuration control are generally client-only things usually. So I mentioned the EPICS community. I'll talk a little bit now about the organization and what sorts of things the community actually does. It's a fairly informal leadership. And Bob D'Alessio is still he's the controls group leader for NSLS2 at Brookhaven, and he's the sort of the informal leader of EPICS as far as anybody is. As I said, he was the original author of GTACS and EPICS, and some of the code still has his name on it, but actually less and less as things get rewritten. He's mostly responsible for community development, so he talks to people about the sorts of things that they're doing and organizes the collaboration meetings. He's very much aware of what many of the labs are working on, if they're creating new programs and so on. He tries to know what they're doing and introduces people. This lab is working on something like that. Have you talked to so and so? So he's a very good people person for that kind of things. In as much as anybody else is leader, I guess I'm probably the only other formal leader that the community might notice. I manage the website and the mailing lists and so on using the APS facilities here. And I also manage and I'm the lead for maintaining EPICS-BAST, the core version 3 software. But a lot of the work on that does get done by other people. So I wouldn't regard myself as particularly a leader as very much, but other people seem to think I am. So then there are a number of other informal development working groups that have their own leadership. So I've mentioned the EPICS version 4 working group. The guy who's mainly working on leading that is Greg White, who's an engineering physicist at SLAC. I co-chair that group with him, but he has experience with the W3C, the World Wide Web Consortium, and with formal standards development and so on. So he's very useful in that regard. And he's also developing version 4 physics code for SLAC for LCLS2 and so on. So they're actually making use of that V4 stuff. I'll come back to that later. There's a group that work on Control System Studio, which is one of the client groups of software for client tools. And nominally, Eric Berryman at FRIB at Michigan State is the group leader for that. But again, that's a very informal group, so I don't think they have particular formal management. There's a group called DISCS, Distributed Information Services for Control Systems, and as far as I can see, that's also run from Michigan State University by a guy called Vasu Vupala, and they're actually working on their equivalent of things like the ERMIS operational database that we use here at the APS, and electronic logbooks and those kinds of things. So that's what one of the areas that group is working in. And then there is also a small informal group working on area detector. So Mark Rivers, the author of that code, is obviously the leader of that. I'm not sure that he would even regard that as a working group, but they do actually have online meetings now, so that's sort of a working group as far as I'm concerned. The Tech Talk mailing list that I mentioned, back in the day when it started, it was called a mail exploder. I don't think you could use that terminology nowadays. It might be a bit dangerous. But so it's a public mailing list, free to join, and as I said, we have around 700, just over 700 subscribers now. If non-members do post, then those messages get moderated, and I do actually clean up spam every day. But the group, so as a result, the group has a pretty high signal-to-noise ratio, and everything from very beginners up to fairly technical discussions on characteristics of new pieces of software or new techniques and so on. We use GNU Mailman to handle subscription, thanks to the IT department here for for providing those facilities, and that can also provide a daily digest if you don't want to read every message as it comes through. I have archives for that mailing list going back to 1994. Last year we had of the order of 2,500 messages a year, so it's a fairly high number of messages. There's also an RSS feed that I generate of the message subjects, so if you don't want to belong to the mailing list, you can actually still see what's going on. And as I said, the questions and discussion occur at all levels, and most members are usually very helpful at trying to understand or answer questions from beginners and experts. Other things in the community then, the website. So the standard EPICS website, I haven't tried recently, and now with Google the searches are, it's kind of hard to tell whether Google is just playing to my to the fact that it knows I'm associated with EPICS, but whenever I do a search on EPICS, Google generally puts EPICS as first, although there are other projects called EPICS now. So the website then is flat file using PHPs, templates, and it's been pretty much the same shape since about 2000 when I created it as a directory for OPEX content. It's really was really meant more as a series of pointers to elsewhere, but there is actually quite a lot of content that we provide now as well. But there are still many links to other sites that provide software that we categorize under extensions, which is client tools, or modules, which is really IOC device drivers, and distributions, which will be collections of software. There is a database on the website of supported hardware, so if you are a developer of EPICS device support, you're actually writing stuff to actually talk to new pieces of equipment, I ask you to enter your data into that website. There's an online form there which will allow me to enter the data into that database. Currently we have over 500 entries in that database, and that's just of the hardware. Then there's additional part that has software, device support, and things that run in the IOC but that aren't talking to hardware. Unfortunately, with the website, only the APS staff, and it's usually only me or that can edit those website pages. So we also have a wiki which is linked from the main site using MediaWiki, and that has miscellaneous frequently asked questions documents and how-tos and those kinds of things. And I do actually make accounts for that available to anybody who in the community who asks. So I can get other people to put things up there if they want. So this is what the website looks like today. It's a little bit clunky, but it works, and I don't have time to improve it at this point. We also have other web services that we use for version control and continuous integration. Early on, when BASE first started, they were using SCCS for their version control. Some of you will never have heard of SCCS. You really don't want to know anything about it. In 1990, the APS staff imported that code into CVS, lost any of the SCCS history that they had, and it was used in CVS then for 19 years, and eventually in December 2009. We converted all that CVS history, including all the commit logs and so on, into a distributed version control system called Bazaar. Nowadays, I would probably pick Git, but Bazaar was, I had my reasons for picking that at the time. And Bazaar has an associated website connected to it. It's run by Canonical, the people who produce Ubuntu Linux. Launchpad.net, which actually provides free hosting of branches, but also provides some nice code review facilities and a bug tracker and so on. So we make use of that Launchpad facility for the EPICS-based software at least. The EPICS extensions, programs, and support modules, that at least the ones that we produced here at APS, are still managed in our CVS repository. You can we have a CVS web installation which allows you to actually access the history if you want to look at the history of commits and things, and also nightly snapshots of the latest CVS commit published nightly, so that people can get hold of that if they need to. But that code isn't changing as much now as it used to. Eventually it'll probably get converted into Bazaar or Git or something like that, but when we have time to do that. We also have, a bit more recently, a Jenkins continuous integration server where we automatically build and run tests on newly committed code for EPICS base, and all the extensions now also get that continuous integration. And also Area Detector and ASIN, they're also using our Jenkins server. And we do those builds on Linux, 32-bit and 64-bit, and also 32 and 64-bit Windows, depending on the project as to which it actually uses. We're also using Jenkins for EPICS version 4 as well, so there are a number of projects in there. So this is just the set of the EPICS jobs on our Jenkins server here. And that's, there's actually a very long list here. I haven't really counted how many we have, but it's certainly very useful for finding problems. Other sites, other places where we host source code. APS has a Subversion server, and the Synapse modules. The Synapse project uses. Actually, there are two Subversion servers. Synapse uses one of those two, and I think BCDA guys and other cats also make use of our Subversion servers here. There are a number of EPICS projects that actually live on SourceForge. So the EPICS version 4 development is called PV Data Devel, and that's using Mercurial. And again, the code lives on SourceForge. And there's also other projects. There's a large one called EPICS Applications, which actually has a collection of a number of different projects that have all sort of all joined on that one SourceForge project. So there's multiple pieces of software kept in the same area, and they use both Subversion and CVS. But up and coming, GitHub and Git is becoming the popular place to store that. So Area Detector, the version 2 of Area Detector is now using GitHub. There's an EPICS Debian project up there, the PyEPICS that Matt Newville will be talking about later in this course. That's hosted there, and so on. Okay, the APS, what parts of EPICS are we using here? So within the accelerators, then we have a combination of VME IOCs running various versions of EPICS back to 3.13.10, sorry, and some embedded IOCs on something called a UCDIM, which is a credit card-sized processor with a 68,000 processor running EPICS with the Artems real-time operating system. And also the accelerator has a number of, like well over 100 soft IOCs running on Red Hat Linux, again, various versions of EPICS. That's one of the things about EPICS. Different versions can communicate. Channel access is very careful to make sure that different versions of the software of the client and the server can communicate. And that's always been something we've been very careful about, to make sure that it doesn't matter what version of client you use, you can talk to any IOC. As long as you can obviously use the facilities of those particular versions, the latest facilities of those particular versions of the software, but you can communicate with any release. And the accelerator, the controls people also have a few soft IOCs running on Windows. That's, I think, mostly the vibration monitoring equipment out around the ring is on Windows machines. Within those IOCs, we have a large collection of record types, some of them taken from Synapse, some of them custom developed, devices and driver support for all the various different hardware that we've got installed out here. All the accelerator IOCs have a standard set of records that they provide their identification and their current status. And when they come up, they update the list of all their process variable names to a file on the file server, so that the system tools can actually look and see which PVs are around, and can query those files and make further use of them. And we also provide terminal servers connected to all our IOCs, so that the controls engineers and operators can actually log into the console and do diagnostics of any problems that they're seeing and see errors and so on, and remotely reset them. On the client side, the Accelerator, the control room workstations are now all running Linux, Red Hat, and most of our GUI screens are written in MEDM. I think we have one or two places where there are some EDM screens, because that's talking to a piece of equipment from a manufacturer that provided EDM screens for us. We use Alarm Handler for alarm monitoring, and the operators themselves actually develop the alarm configurations for the Alarm Handler. The software and high-level software, scientific software, is based on SDDS, the self-describing, I can't, anyway, those of you that know what that means, and TickleTK, so data sets, self-describing data sets, which was software developed by Michael Borland and his team when he was in OAG here. And the archiving of the accelerated data is done by SDDS data loggers, which is unusual. Most of the other EPICS sites don't use SDDS. They have a separate program for doing archiving. And another interesting thing is the run control system that we have, which is a sort of a reservation system to make sure that you can't have two copies of the higher level control applications that are trying to control the same pieces of equipment at the same time. We also have a numbered installation system so that the operators can roll back if they find the new version of MEDM breaks some of the screens, something like that. They can very easily and quickly roll back to the previous version where it was working, without having to call on the controls group or Janet to rebuild it. We also use PV gateways. There are PV gateways around the ring, and also one between the office networks and the Accelerator network, to allow scientists and engineers read-only access to live data. But you have to be inside the Accelerator subnet to actually be able to modify and control the Accelerator itself. So many of you will have seen these are the kinds of screens that we have here. So this is just a collection of screens that I picked out for the APS Linac. There's the L3 chicane and all that sort of stuff. I really don't know what's on that stuff on that page, but those are the sorts of things that we use in the control room here. On the beamlines, and really I'm only talking about BCDA systems here. A lot of those are VME-based IOCs again, PowerPCs running VxWorks. There are also some things called the EPICS Brick, which is a PC104 or PC104 Plus system running on Vector Linux, and we have IOCs running there, and also soft IOCs. Mainly, those are used for area detector taking images from detectors. All the record types, device support, and database templates are provided by Synapse. So Tim Mooney's software and BCDA group putting that collection together. Tim tells me that not all of the IOCs, but some of the IOCs do actually also publish their standard identification and status PVs, and I'm obviously meant to fill out that bullet point and didn't, so they have this thing called the Alive record, which is just coming in to, again, provide status of what the IOC is doing, I think, and make sure it's still working. And similarly to the Accelerator then, there are terminal servers for most of the IOCs so that you can access the console and do remote diagnostics and remote reset as necessary. I know less about BCDA client side, but I believe most of the Beamline workstations are running Linux, although there are a few Windows PCs around. Those are probably mostly for camera drivers. Most places are still using MEDM, although I believe there's at least one cat that's using Control System Studio now, or at least experimentally at least. Different Beamlines use different kinds of client software, so some of them are using spec. There are the TXM and the tomographic Tomo UI. Other sites are using ScanC, and then there's also IDL programs and custom Python code and so on. So it's basically a very wide collection of ways of taking scientific data and managing the systems. And similarly, the PV gateways are used here. We actually have gateways between the Accelerator subnet and the IOCs and the Beamline subnets, so that the Beamlines can access PVs that are relevant to that particular Beamline and control the gap and so on of their undulator. So they have limited access into the Accelerator network. So here's the gratuitous snapshot that I was able to find of TXM ScanOcean. There are then some other choices, things that we're not really using here. Control System Studio is one of the major applications. It's a collection. Control System Studio itself is an Eclipse rich client program application, and it's basically a shell into which you can add your own tools or plug-in tools. And the main tools that that are used within this are basically integrate together very well, because Control System Studio provides these integration points. So the BOY, WYSIWYG editor and runtime for display screens, their user interface tool, you can actually click on a widget shown in BOY and right-click on there and pull up a menu item there that says, show me that signal in the data browser. So that's another one of the plugins, and that allows you to plot live data and also fetch archive data for that particular signal from the archiver over time, so that you've actually got integration very, very easily between those two tools. There are other tools like Probe and PV Table, which let you interact with and modify individual PVs or groups of PVs. And to save you having to do a lot of typing, they have autocomplete built into this stuff, so that you can actually start typing PV names and it'll show you a list of ones that you've used recently. And there are extensions to that autocomplete that allow you to actually query a local process variable. The equivalent to the alarm handler in Control System Studio world is this thing called BEAST, which does alarm monitoring and acknowledgement. And then they also have interfaces to control their archiving system. So there are a number of different archive programs that can be talked to and controlled from Control System Studio. So the channel archiver is one of the older ones. I'll talk a bit more about archivers later. They archive into databases, and there's also a new one which is really rather nice. It looks like it's going to be rather nice, called the Archive Appliance. There are interfaces to their electronic logbook systems, so you can actually record information in your permanent electronic logbook and actually specify attachments. You can pull things from your data browser or your screenshots and so on, attach those to your log entries. And there's also at SNS they have a scan server where they can actually do experimental scanning. So Beamline experiments can use the scan server to set up experiments and run scans of equipment. So I have a few more screenshots here now. So the ITER program in Europe, in France, is using CSS-BOY. So here's one of, I have a couple of screenshots from them. I'm not sure what these, okay, Fast Plant System Controller Operating Interface Main Menu. So their screens look rather different to our screens. Obviously, this is, I think, in some cases, mock-ups for screens that they're planning on. At SNS, they use CSS-BOY again, in the main control room, they also have a number of EDM screens, but here's an example of one of their main screens. And they also use this BEAST tool, their alarm status tool. So this is an annotated image showing you that, okay, so you have got a list of the alarm tree on the left-hand side, and that shows you the status of the various different parts of the machine, and then they can drill down into the alarm table down there so that you can then pick a particular alarm. So the table shows you all the current alarms, and you can drill down into that and then use the data browser to look at the history of the channel that's in an alarm and look at what it's doing, why it's in that, what its history was, how it got to the alarm state, and so on, which is an integration that we don't have as well with the alarm handler here. Then, in addition to Control Systems Studio, one of the other technologies, which is it's not mature yet, but is being worked on, is a development called EPICS. This is an initiative that now has some SBIR funding, and they're developing a CSS-like framework to build EPICS client tools using the cross-platform Qt toolkit. Now, one of the disadvantages of CSS is it's based on Java and the JVM, and it's fairly monolithic and big. EPICS Qt is highly portable to many different platforms. It runs on anything from phones up to big workstations. The EPICS Qt initiative is basing their work on the EPICS Qt display manager, who Andrew Ryder from the Australian Synchrotron created. But they've now they've included him in the project, and a guy, Anton Metzger from PSI, who also had a Qt-based display manager, and he wrote a lot of tools to actually take MEDM screens and import them into the Qt environment, and that's compatible both with between his tool and Andrew Ryder's tool. So the EPICS Qt looks like they're going to be developing some new and nice tools if their plans actually come to fruition. As I said, Qt is actually widely used by industry, and it's sort of seems to be the last major cross-platform widget tool set that's not specific to a particular manufacturer anymore. I wasn't able to find an EPICS Qt screenshots, but here's one from caQtDM, so it's sort of showing you that it looks pretty much like all the other control room type screenshots, but they can do those kinds of things in the Qt tools. We also have, there are some other tools that mostly, again, I'm talking about things here that mostly we're not using here at APS. As I mentioned earlier, we use SDDS for an SDDS logger for doing data archiving. Most sites actually have a dedicated data archiver, and that's actually gone through many different iterations over the years. So the original was AR and ARR, and I have a feeling that may have been used here in the early days. Los Alamos wrote this thing called the channel archiver, and that's gone through various iterations. That was higher performance than the original archiver, and that had an index for doing data retrieval so that you could actually find your data reasonably quickly. I don't know anything very much about MYA and Caesar, but there they were actually starting to use a relational database for that index, and then they actually started putting the data into it into the relational database as well. But then there were started to be problems with performance on that. So Beauty came along, and that's related to Control Systems Studio, and that was using a partitioned relational database to store the index and the data. And then someone came along with the idea of using Hypertable to actually store your index and data, but still with an RDB for configuration. So the hyperarchiver came along. And the latest one from Slack, which looks very interesting, is something called the Archive Appliance. The idea there is it's very scalable. You can basically just add a new appliance and add your new process variable names to that archiver. And it's designed to have zero oversight, and that seems to be, it's also designed around modern file systems. So some of these previous ones, the problems why they went to relational databases was because the file systems were not very good at writing data continuously. to various different parts of the same file because you're searching between file systems and so on. So, but the file systems are actually making things easier and better for that nowadays. So the archive appliance, I think, requires you to have either the ZFS or what's the Oracle one called? Anyway, basically the new modern Linux file systems. The other thing that I thought I would mention here, I've mentioned that we use the PV gateway to connect between subnets, but there are some limitations on that. So if your data actually needs, you need high performance for large arrays, then there's another gateway that's been written at the Swiss light source, PSI, called the EPICS Sharp gateway. That doesn't work as a gateway at the same level, but it actually has much better performance with large arrays. But unfortunately, that's written in C# and designed to run on Windows. It doesn't use our standard channel access libraries, so I'm slightly wary of trying to use that unless you know what you're doing. And then finally, I need to mention that EPICS development continues. So the version 4 working group has been working for several years now on a replacement protocol, network protocol for channel access called PV Access. And the design ideas for this are to be able to efficiently transport any kind of structured data. So currently with channel access, you're limited to a value or an array of values plus some attributes associated with it. PV Access has this data layer called PV Data, which allows you to introspect and create a structure of any kind. But we need to retain channel access's very high performance and the publish-subscribe architecture that it's using, but add capabilities like remote procedure calls for or command response type things. Now, if you just put together data structures and say any kind of data structure is valid, you then find that your clients can't talk to, your general purpose clients can't talk to your new IOCs, those kinds of things. So as part of this version 4 work, they're actually defining some type standards where there'll be some standard normative type data types for structured data, so that if you have a collection of things, say an archive will always produce data in a specific type if it's going to meet the standard, and then all your archive viewers expect to see that kind of data type from the server. And similarly, so there are things like the normative type data tables, and I can't remember all the other types, but there are specific types that are useful, are seen as useful in our industry. And there are implementations of this code in both C++ and Java. Now, both Marty Kramer and Bob D'Alessio, who originally developed EPICS, are involved in this development work, so they know what they're doing. And the latest version of Control System Studio already talks PV Access, so it's possible to make use of this. And several labs are very interested in working on it. Brookhaven NSLS2 are using it for communicating their higher level application protocol, is going to be PV Access. Slack is developing physics applications for LCLS2 and their modeling and so on using this. And there are also development effort and attempts to use this at both ITER and Diamond. Diamond have been putting PV Access on top of area detector so that you can actually take an area detector image, put the PV Access server on top of your area detector camera, ship the data over PV Access to another machine where there's a PV Access client that looks like an area detector camera. So now you can farm that data out and do processing on a different processor, and so you can actually do image processing and make yourself an image pipeline nicely, quite easily, and get good performance